Hello everyone, I hope you're doing well. This is Krishna from Sony. So in this presentation, I will present this paper titled Neat Neural Attention Fields for End-to-End Autonomous Driving. Now, when I selected this paper, I thought it was about something related to obstacle avoidance or some novel reinforcement learning or control-based algorithm or something like that, but it is not. I will go over the details. So this paper was accepted in ICCV 2021 and comes from Max Planck Institute for Intelligent System Tubingen and University of Tubingen collaboration. So moving on. So this work presents, as the title suggests, neural attention fields, in short NEAT, and this is a novel representation learning method that enables scene understanding for end-to-end imitation learning models for the task of autonomous driving. Essentially, what NEAT is that it's an implicit representation learning function that maps location in bird's eye view scene coordinates to waypoints and scene semantics using intermediate attention maps to iteratively compress high-dimensional 2D image features into compact representation. And NEAT outperforms several baseline and achieves driving score on par with the privileged Carla expert that is used to generate its training data. So the training data is essentially generated using this privileged Carla expert, but the details of this privileged Carla expert is not provided in the paper. So this is just an unknown expert that they somehow get the data from somewhere. And furthermore, they visualize the attention map for that the model learns is an intermediate output, and it shows interpretability of what the model is learning. So that's what they present here. So again, the paper explanation will be split in 4 parts, and I will go over the points in brief and then cover the details later on. So let's proceed with the high level overview. So why is this method important is that the navigating large scale dynamics scenes for autonomous driving requires a meaningful representation of both the spatial and temporal aspects of the scene. They learn a representation that captures bird's eye view scene semantics and trajectory information. The aim here is that this representation would improve the performance of an imitation learning based agent. And they say that BEV or bird's eye view based scene representation learning had only been possible with expensive LiDAR and HD map based network inputs, which could easily be projected into the BEV coordinate frame, but here they leverage implicit representation based method and they essentially propose a novel method which makes it possible with image modalities as well. So this is what their approach looks like. So this is what their architecture looks like. So they have an encoder which is essentially a ResNet based model, and this encoder for different images, it gives these feature vectors which are then concatenated and with positional embedding and velocity embedding and fed to transformer, which is then used as input to train this neural attention field model. So the input to this neural attention field is xyt, x dash y dash. Here xyt is a point that is sampled in the vicinity of the moving vehicle, and x dash y dash is the target location that's specified by some navigational system such as GPS, etc. And it predicts an intermediate representation which is then concatenated with the transformer output, and then this step is performed in a recurrent manner to predict this offset. So to predict this offset is essentially a different way of predicting the waypoint, and it also predicts the scene semantics, the semantic segmentation of a scene in bird eye view coordinate system, and then they are supervised with different losses, the L1 loss and CE loss, and after this network is trained, these waypoints and semantic scene segmentations are then converted to the different or autonomous to the vehicle parameters such as steering, brake, etc. values using a controller, lateral PID and longitudinal PID, and that is then used to drive the car. I will go over the details again later on. So this is just a basic result of what they are able to do. So for a given, as the vehicle, as this guy, as this man is it is moving, as the vehicle is moving, as you can see. So we are essentially in the coordinate frame of the vehicle. We see what the vehicle is seeing, and around the vehicle the semantic segmentation is being predicted in bird eye view semantics, and these waypoints are predictive, which is visualized in the form of these offsets. And so this is how I will again cover the more in a more detailed understanding. So they use a simulated, so they use Carla, which is an open source simulator for autonomous driving. It is a simulation platform that supports flexible specification of sensor suits and environmental condition, and it provides full control of different dynamic and static objects in the scene, and it also gives several other control. It also allows control of several other features of the environment such as maps, and it provides different digital assets such as urban layout, buildings, vehicles, and it's open source, so it can be used freely to generate different kind of environment and can be combined with different experts as well. So how exactly is this working here is, so I talked about waypoint. What exactly is a waypoint is, the waypoint is defined as the position of the vehicle in the expert demonstration at time t. So as I mentioned before, we are dealing with imitation learning based agent here. So what happens is that given a data set of expert trajectories, so expert is an agent that is very efficient or that performs very well in that given environment, and we train a behavior cloning agent through supervised learning, where the goal is to predict the action of the expert given some sensory input regarding the scene. So here the waypoint at a given time is essentially the position of where the vehicle will be in the expert if the expert was completely controlling that vehicle. And because we are predicting everything in bird eye view coordinate system, so waypoint is the position that is projected in the bird eye view system of the vehicle's local coordinate system. So by the vehicle's local coordinate system, what we mean is that the coordinate system is defined in such a way that the vehicle, that at any time the origin of that coordinate system is the center of the vehicle, and where center of the vehicle at that given time, and the front of the vehicle is aligned with positive y-axis, and waypoints form a sequence. So what these waypoints are is, as we said, it's the position of vehicle in the expert demonstration. So these waypoints from future time steps can form a trajectory guidance that can be used to control the vehicle, especially during training. So as the agent drives through the scene, sensor data is collected. So the sensor here is just an RGB camera. So here we have three cameras, one is oriented forward and the other is oriented 60 degree to the left and right of vehicle, and these three cameras together provide a 180 degree view in front of the vehicle. So it seems like, yeah, in this specific case the vehicle does not go into reverse gear or take back turns or something like that. So while neat can be, as they say, can be applied with different buffer sizes, the focus here is that the input is just a single frame. So at any given point, at any given forward pass of the network, they use three images as input because they are only using the view at the current time step. They are not using views that was initially there or what the vehicle was initially seeing, because apparently historical observations show that keeping history into mind while driving can be detrimental. So related work, so they have a dynamic, so implicit scene representation. They use implicit scene representation, and so essentially what they're doing is they have a dynamic coordinate system, as I said earlier in the previous slide, in which the car's location at a given time is set as the origin, and they map the 5D input, which comprises the XY location around the car and at the time at which we are sampling these XY location, and the target location provided by GPS, and that is mapped to the waypoints and semantic segmentation output of the scene. So because it's taking into account XY, which is sampled across the car, it is taking into account the environment, the scene, it is taking into the semantics of the scene is being taken into account while learning the representation, and it is also taking into account the target location that's provided by GPS. So it's also taking the target trajectory into account. So that is why this representation is able to capture both scene semantics as well as the target trajectory it should be taking. So another related work is end-to-end autonomous driving. So there are various methods for training an end-to-end autonomous driving agent, but in this method they are mainly focusing on imitation learning method, which they say is state of the art for several autonomous driving related tasks. So they mainly focus on them in this paper. They show that NEAT can help improve the performance of implicit learning based agent. So there have been other works as well that have used BEV semantics for driving. So why do they model scene semantics in bird eye view coordinate system? Is that they say that a top down view, so if this is the car here and this is the environment, so this is essentially, this view is the bird eye view of the given scene. So why they are using bird eye view is that a top down view of a street scene, they say, can be powerful for learning driving tasks, since it contains information regarding the 3D scene layout and objects do not occlude each other. Like in this coordinate system hardly anything is visible, and in this system, so I'm not sure what's the issue with this system, but they use a BEV system anyways. And in BEV system objects do not occlude each other, which is true, and it represents an orthographic projection of the physical 3D space, which is better correlated with the vehicle motion and kinematics than the projected 2D image domain. I'm not entirely sure if that's true, because I mean humans don't exactly drive using bird eye view system, but they say that it has been shown to better capture the 3D space and really correlate with the vehicle kinematics. So yeah, that might be the reason why they are doing it. So this is the method overview that I mentioned earlier as well. So as I said, they use 3 sensors. So one that is aligned along the vehicle, and 2 cameras at 60 degrees. So essentially at any given time we can have a 180-degree view in front of the vehicle, and each of the 3 images is passed through a ResNet, which is then combined with certain positional and velocity based embedding and passed through a transformer. So why do they use a transformer here and not just directly pass it through this neural attention field? They show it in their ablation study that adding a transformer does improve the results. So but in terms of the intuition of why they are doing it, is the goal of the transformer here is to integrate features globally and adding contextual cues to each patch with its self-attention mechanism. So this enables interaction between features across different images and over a large spatial range. Essentially it finds correlation between each patch of the features that has been predicted by this ResNet. And and as I said, and it was shown in ablation study that it does improve the performance. So while the transformer aggregates these features globally, this transformer is still not taking into account these x dash y dash or the target location, and it's essentially not, yeah, so this is not taking the trajectory information into account yet. So that's where here NEAT, or this neural attention field, comes into play. The goal of this neural attention field is to learn a two-dimensional offset vector as from a query location. So essentially they have to predict waypoint, which is this W, but they are predicting offset to waypoint and they are not predicting waypoint. So why are they doing that is that they want to use the same network for predicting this semantic segmentation map and the waypoints as well, but this segmentation map is a dense prediction. They have to predict none, road, obstacle, red light, green light for every pixel in that, for every location, but waypoint is just at a given time t, it's just where the vehicle will be in an expert demonstration. So the waypoint, the ground truth waypoint, is converted into offset. So for every location, the difference between the waypoint position and that location is computed to get this dense offset map, and then they are able to use the same network for predicting semantic segmentation map as well as offset, because they want this network to capture the information of target and as well as the scene semantics, so that they using as so that's what their intuition here is of using offset and not waypoints directly. So what they do here is essentially that future waypoints along different, and also another reason is why they are using this target location at all. So the future waypoints along different trajectories are plausible, so thus it is important to adapt this waypoint based on the driver intention. So they do this by providing this target location as input, and as I said before, the target location is nothing but GPS coordinates provided by navigational system along the route that is to be followed. And yes, everything is transformed in the same coordinate system as the waypoints, and which is the same coordinate system that I said before. So for any given time t, NEAT predicts waypoint for certain time steps into the future. Now this time step into the future, it's now how many time steps into the future is a hyperparameter which is fixed. And so in this work, which is actually that hyperparameter is set as 2. So they predict the waypoints for 2 time steps into the future, and that is then used to guide the motion of the vehicle. Now the ground truth for the waypoints can be obtained for an arbitrarily large time steps in this case, because we are dealing with a simulated environment, but they choose a fixed time horizon as it shows better results. They show that in their ablation study as well. So, and yeah, as I mentioned about these offset to waypoints, now in addition to waypoints, they also use bird eye view semantic segmentation map prediction as an auxiliary task to improve driving performance. So, and as I said that, yeah, so they will use the same network for predicting the bird eye view segmentation map as well as the different offset to the waypoints. And for the segmentation, they have 5 classes basically. So none means nothing here. Yeah, purple here is road, it's either obstacle, or red and green light. So red and green light's location is known because it's a simulated environment, and they create a certain radius around each location of red and green light to provide more answer to maybe not force the network to regress the exact location, but somewhere around it to make the task easier as well. So sampling, so I have not mentioned about how to query samples and create ground truth for the queried points. So how do I do that is that at any given location at a particular time, the target location is fixed, but XYT can be varied to access different locations of the scene. the waypoint information is only available, so there is an issue with that the waypoint information is only available at discrete time steps, and segmentation labels are only available at discrete spatial locations. But keeping these in mind, essentially what the authors do is that they only supervise the neat model at discrete points in space-time volume. So even if they are predicting segmentation label at a spatial location for which they might not have the ground truth label, they'll only supervise it at locations for which they do have the labels. So what they are doing, again, as I mentioned, 5 classes are considered. So as this is a simulated environment, they have every information about what each point corresponds to, and they make sure that they are sampling points from each of these locations in a way that avoids imbalance of different class as much as possible. Of course, completely avoiding class imbalance might not be possible every time, so they gave importance to the classes which is represented least in the given frame at that particular time step. So that is how they sample points to make sure that they do have information about segmentation labels, and they do have information about waypoint as well. So this is what the training objective looks like. So this is basically L1 loss between predicted wave offset and the ground truth offset, and cross entropy loss between predicted semantic class and ground truth semantic class. And yeah, the different parameters such as lambda, gamma, m and n are varied and are tested, and in ablation study they show why they select which parameters, the parameters that they do. So the controller, at test time, the waypoints and red light prediction from the model are converted into steer, throttle and brake values, which are then used to drive the vehicle. For a red light, they sample a sparse grid around the vehicle, and because they actually created a radius around red and green lights, even a sparse grid was enough to accurately detect red light in the scene, and a relatively dense grid was sampled for predicting waypoint. So to obtain the throttle and brake values, they compute vector between waypoints of consecutive time step, and the magnitude of these vectors was fed to a PID controller with red light indicator, so which indicated the vehicle should stop in case of a red light, and the orientation of this waypoints was used as input to lateral PID controller for turns. So this was done in a relatively deterministic manner. So a certain version of Carla, which is a relatively latest version, 0.9.10 was used. Training data was generated using expert data along routes from 8 publicly available towns, and test data was they had two types of test data. One was the official Carla leaderboard, and the other was an internal evaluation, and these internal evaluation routes, they were custom made by the authors themselves. So that had 6 different town settings, 7 different weather conditions, and 6 different daylight conditions. So these are some of the visualization of the internal routes. So for example, this is a town setting. The red is the start point, blue is the end point, and green is the trajectory that needs to be followed by the vehicle. And these are different evaluation routes shown here. So the internal evaluation baseline, they compare their work with different base methods. So this expert is the expert that they use their imitation learning model to match, but there is no information about this expert. So this CILRS model was state of the art in Carla 0.8.4, and then LBC was state of the art in 0.9.6, and then these were AIM was a model that was improved, that was proposed as an improvement of this model, but it used a GRU based decoder. And then they proposed different variants of this model, in which they augmented this model with certain auxiliary tasks such as semantic segmentation, BEV semantic segmentation, and 2D depth estimation. And again, so instead of using semantic segmentation as an auxiliary task in one of the baseline, they use semantic segmentation as an input to update the waypoint predictions. So they compare with different baselines, and these were they compare the baselines across these three metrics. So one was the route completion, so percentage of route distance, which is defined as the percentage of route distance completed by the agent before it deviates from the route or gets blocked. The infraction score was basically how safely the car can drive, so how safely does it drive without violating rules in regards to this collision, lane infraction, red light violation and everything. And this is how the penalties were applied, and then they were multiplied like that. So this is the formula used for this. PI is the infraction score, and the driving score was route completion weighted by the in the infraction score. So this is how we would define the, and this is averaged across different routes. So n here is 42 in case of internal evaluation, and official Carla leaderboard, I'm not exactly sure how many routes were there in the official leaderboard. So this is the, in left table shows the comparison on internal routes, and and their model does best in terms of infraction scores. So they claim that their model is the best in terms of driving safely and also in terms of driving score in internal evaluation. But in official leaderboard, their method here amongst the baseline, it ranks at number 3 here in terms of driving score in comparison, and they compare here with other works. And in terms of route completion, it seems to be inferior to a lot of the baseline, but it's apparently really safe in terms of this infraction score. It does not violate a lot of rules, because of which it obtains a relatively high driving score. And they say that because some of these methods are not relying on bird eye view semantic segmentation, they are prone to making more infractions and rules breaking. And so one of the strange thing here is that it was AIMMT was the auxiliary tasks were changed, and it did best with 2D segmentation in terms of route completion and not with bird eye view segmentation. So it seems like that in terms that bird eye view segmentation, while results in better infraction score, it seems to come at the cost of route completion. I'm not exactly sure why that is the reason, but that's what the results seem to be suggesting, and it's quite consistently seen across the two leaderboards. So they showed effects of changing different parameters. So I said earlier that they use a fixed time horizon of 2. They show here if they use a time horizon of 1 or 3, the performance is quite inferior than when they use a horizon of time 2, which it's quite strange result, but that's what is being suggested. And no transformer is shown here in this one, and it's inferior to what their default model seems to be performing in comparison to that. And so again, different parameters are compared, and effect of different components of architecture are shown, and their default configuration seems to be the best way to go about it. And they also said that their attention map provides a certain degree of interpretability, and you can see here that here if in this segmentation map, this is the input, and you can see that here the activation is really high when there is a person in front, and in the activation is high in case of here it's a lane here. So I mean, it's not exactly interpretable, but there is certain degree of interpretability involved is what they are saying here. It's there is a high activation for this green light, and here we have a high activation for the red light, which is possibly present here. So this is just a visualization of what this is the neat output. So this is the semantic map that's predicted, and this is the waypoint that's predicted, dense waypoint prediction, which is predicted as an offset to waypoint actually. And this is the location, this is predicted waypoint, and this is the target location. So it slowly proceeds towards the target location. So again, this is a comparison of segmentation map. And so discussion of this is, I'm not exactly sure BEV based approach is the best way to go about it. I mean, they do explain that it has better correlation with vehicle kinematics and there is no occlusion, but in terms of some of the results that were shown with route completion metric especially, I'm not sure it's the best way to go about it. and there are lack of explanation for certain results, especially in terms of ablation study and in terms of how exactly their model compares with certain baselines. And some of the pros is that there's partially interpretable attention map, and their model, it's a relatively simple controller, has been used, suggesting potential growth and ability to be combined with other imitation learning based methods as well. So that's quite good. And another con which I have not mentioned is that we don't have any information about the expert that they use. And if we compare the results here, so the expert, and actually they outperform the expert here in terms of driving scores. So maybe if they use a better expert, or if they combine it with other works, their methods might improve further. So that might be a potential room for improvement there as well. So this is basically the end of the presentation. Thank you so much for watching.